Hello, everyone. I'm talking today about some of my group's work on efficient wireless sensing. I'm an associate professor at UVA in computer science and electrical and computer engineering. And to sort of give context to what I want to describe today, I want to start with a couple of the test beds that we're running at the University of Virginia. So first one, sort of on top here, is what we call the Living Link Lab. So this is a fully instrumented space in where my office is. We have about 100 grad students with desks in this space, as well as a common area kitchen and meeting rooms. And over the past few years, we've instrumented this for sensing all the various properties of the building, including energy consumption, air quality, occupancy, and other sort of parameters of how the space is used. And the goal here is to be able to do in situ research looking at not just how the building is operating, but how that interfaces and interacts with occupants. This testbed, of course, is an office setting. So it's meant to be a sort of shared collaborative space. That means we have a lot of occupants who have office space, who have desks, but also use the space for on a more transient basis. In parallel with that, we also have a test bed looking at the outdoor space. And so this is along the engineer's way where the engineering buildings are, monitoring air quality and temperature and humidity of properties sort of outdoors as sort of a complement to the indoor test bed. And when you build a test bed like either of these, you sort of realize pretty quickly that unless you want to have somebody go around to every device every day or so, having the right wireless connectivity is essential. Now, there's always trade-offs. Anytime we choose a wireless protocol, often these are in terms of cost, like the monetary dollar cost of using it, or it's in terms of energy and how often we need to replace batteries potentially. But whatever we choose, there's always these trade-offs, and it really helps to have kind of the right technology for the right use case. And we can look at this on sort of a couple different scales. And there's different protocols that maybe map to different use cases. So Bluetooth is often good for local nearby devices that may be a room scale. Wi-Fi and an emerging protocol called Thread are designed for multi-hop connectivity among many devices, perhaps at sort of a building scale level. And then another protocol gaining traction is called LoRaWAN, and this is really designed more at the city scale, so long-range communication. And depending on what the deployment or the use case is, different wireless protocols start to make sense. And this has kind of led us to say, well, we need to have these wireless protocols so we can relay data back from our devices in real time and then be able to actuate the environment or better monitor the environment continuously. But these wireless signals that we sort of have to use as a way to collect data can also be reused for other purposes. And that leads into this idea of wireless sensing. And so I want to highlight two projects in this area. One is going to be sort of at the building scale, room scale level, and then another at the sort of more city campus scale level. So starting with sort of the smaller building or room scale context here. The use case that we're targeting is occupancy detection. So basically, is there someone in a room or not? Now, this is one of these problems where it's very simple to describe. It's actually very useful. Buildings today are generally operated with sort of fixed schedules. They just assume a certain level of occupancy during certain hours of the day and operate the heating, cooling, ventilation systems, lighting systems sort of based on that. But they're not really responsive to what's actually happening. And for things like air quality, this can actually be significant. And so being able to ventilate and exchange air more frequently when there's actually a lot of people in the room leads to much better health outcomes for occupants. The challenge is, despite this being sort of a easy to describe application, is there someone in a room? Doing this automatically is actually quite challenging. And the reason is because while there's a range of different techniques, they have these pluses and minuses. So traditional PIR, these are motion-based occupancy detectors, are okay, but once you stop moving, they stop detecting and the lights shut off. And that's really annoying. Things like cameras can be very, very accurate, but they require a reliable source of power and they're sort of privacy invasive. Other sensors, like using CO2 as we exhale, can be reasonably effective, but they sort of lag behind. The room has to be occupied, then people exhale, and then we know the room is occupied, which is a little bit too late sometimes. And so that sort of motivated this idea of using wireless techniques. And there's been various approaches for doing this, using sort of signal strength techniques or more advanced CSI-based techniques where we're really digging into the signal of the from different wireless devices in the space. And while there's a different potential here, there's again sort of these trade-offs. And so one thing we wanted to target is, can we lower the cost of doing this sensing while trying to keep the accuracy pretty high? And so to do that, what we noticed is that in more recent versions of Wi-Fi, there's an extension to the protocol called a Wi-Fi fine time measurement. Now, if you're familiar with time of flight two-way ranging protocols, this is basically just that. It's a way for two devices to exchange wireless messages. And the goal really in the protocol is to figure out how far apart those two devices are. So you can think about this, that one device sends a request to the other, the responder then returns a message, and based on the timing of those messages and essentially the speed of light, we can estimate how far apart these two devices are. And this could be useful for things like proximity detection or sort of other localization techniques. However, what's interesting here is that this is sort of baked into the spec. It's included in the hardware, and it's really picking up on some very subtle properties of how those wireless signals are propagating between the two devices. And so rather than be interested in the distance, so in our case, we're going to have two devices, they're actually going to be at a fixed distance apart. We're more interested in how that reading changes based on the presence or lack thereof of occupants. And so what we found out is that if we exchange a few of these messages, and these are, again, standard Wi-Fi messages that you can do with really cheap, like $1 or $2 hardware that's easy to buy. So this is sort of a low overhead method of occupancy detection. And then we can use this mechanism, send these signals back and forth a few times, measure what they compute the distance to be, and actually use that to determine if someone's there. And the key is that while the devices are a fixed distance apart, they're not moving. When people are nearby, because our bodies have a little bit of interference with the wireless signals, the measurement these devices will record actually changes a bit as we're present there. And so as we move even just a little bit in the space, the recordings of these fine time measurements or these distance measurements will actually change over time. And so if we collect this on a few different channels to cancel out certain errors that would only be present on certain wireless channels over the course of about a second or two, we can actually use this as the input to a classifier to detect whether or not somebody's in that room. And so we went and tried this out. Right? So we have this test bed. We wanted to add this capability. So you can see one of the rooms in the link lab here. We've got a traditional PIR-based sensor on the ceiling that sort of is probably the most common way that occupancy monitoring is done today. And then we have our Wi-Fi devices in the same space. And basically, we're exchanging the messages, having different people occupy the room for different amount of times, and then looking at the performance of different classifying models to figure out if someone's there. And so what we're interested in is like, how well does this work? In particular, we're interested in what happens if people don't move, right? Those cases where the PIR sensors tend to fail because they just assume the room is empty and turn the lights off on you. And so first, we looked at what happens if we have one person in the space and they're moving a little, right? So we kind of classify this in roughly two different areas. So very fine motion is very subtle movements. Fine motion might be writing where you're sitting still, you're moving just a little bit. And so we find is that with these different motion types, it's still very difficult to detect if someone is really not moving. They're basically just breathing with the spine time measurement. But if you do move a little bit, so basically if you're not sleeping, we still are able to detect the occupancy. And so here we can compare the two different occupant motion types with our models. And even if there's just a little bit of motion, we still have high accuracy with detecting if someone's there. And so this is really helpful for being able to get beyond those PIR motion sensors, which often turn the lights off on us. And to compare those more directly here, what we can see are basically these are the very fine motion and fine motion over time. And the ground truth here is that the room was completely occupied. And so we can see the yellow line on top, that's the PIR sensor. And so it should be detecting occupancy continuously, but it's not, because those subtle motions get lost with that sensor. Whereas here in the blue line, we can see that our approach is able to continuously realize that this room is in fact still occupied. The person hasn't left because they were moving a little bit. Now, one challenge with these type of wireless sensing approaches that are using these machine learning classifiers is that we don't want them to only work on the room that they were initially trained on. So we want to be able to adapt to a different environment. So ideally, we would take the classifier from sort of one space, use that ground truth data to develop the model, and then be able to use it in other rooms. And so we looked at this as well by collecting data in multiple rooms, but you're only using one room's data for the training. And what we see is that this model is sort of picking up on general properties and not overfitting to one individual space. And so if we move the furniture and sort of change the properties of a room, the accuracy remains high. And if we move from one room to a different room, again, the accuracy remains high, sort of giving us some confidence that what this approach is actually detecting are those changes by the person and not something more specific or overfitted to one particular environment. And lastly, we got interested in what happens if we have devices, one device in the room and another device out of the room. And so this kind of gets back to this idea of, can we potentially reuse existing Wi-Fi devices that might be already present to add this new capability? And so here we tested it with having one device in the room where the occupants are, one device outside through a door. And what we see is that without the metal blocking it, the performance stays high. But essentially, the wooden door is more or less invisible to the wireless, which is good. With the obstruction, the performance degrades a little bit, so it's a little bit trickier to do this if you don't have two devices in the room. But we're still able to get a rough approximation of accuracy of occupancy for the room. And so we sort of summarize and look at the different tests we did, different room types over different periods of time with different movement levels. You know, what we see is that a random forest model using this sort of input data has pretty good performance for doing occupancy detection. And again, these are pretty cheap, $1 or $2 Wi-Fi devices. In this case, right now, these are devices sort of dedicated to this occupancy task. So this would be sort of like you stick two devices on the wall, they communicate and provide occupancy information for that room. In the future, we might be able to reuse existing messages or take devices which are already deployed, use this fine time measurement approach, and collect the data without having to deploy additional hardware. And so this is an example of how we can use some sort of off-the-shelf devices, build these sort of wireless sensing techniques, and really try to optimize the performance without having to dedicate a lot of additional hardware resources or energy to this particular sensing task. So that's one approach, looking at sort of the room scale, building scale type use cases. We've also looked at, and this reflects those test beds I was talking about, what happens if we go a little bit bigger, look at sort of city scale or campus scale networks. And to do this, we've been deploying this LoRaWAN network here at UVA. And so here's just a couple pictures of the deployment over time. So our computer science building, we have one of these gateways mounted on top. The computer science building is one of the tallest buildings in the area. And so this is a really strategic place. We have another gateway deployed a little bit further away at the Aerospace Research Lab. Again, sort of same hardware, deploying these LoRa gateways. We recently got one installed at the UVA hospital, which is in a slightly different area. Again, sort of overlooking, you can kind of see the view there. And having these receivers up high really provides really great coverage around Charlottesville. And finally, we've worked with the city of Charlottesville to deploy one of these gateways on top of City Hall. And so this is a reasonably, kind of, it's not that tall of a building, I'll be honest. But for the sort of downtown area, it's pretty good, and sort of, again, gives us coverage downtown. And so these are sort of the backbone to providing this LoRaWAN network. And this figure isn't sort of, is a little bit outdated, but it kind of gives you a sense of, if we sort of go different places in the city, where can we get this network coverage? And so even with just a handful of these gateways sort of strategically located, generally high up in select areas, we're actually able to get data from a wide area of locations without having to deploy extensive amount of this network infrastructure. And LoRaWAN is a really strategic choice for us, because it's really meant to be sort of this open platform where we deploy the infrastructure one time, but then a lot of devices can use those receivers without having to either go through a cellular company or deploy their own infrastructure. And part of that is using the Things Network, which is this open source platform for providing this connectivity. They essentially let individual users contribute gateways like we've done, and then they sort of provide this backend platform so you can add your devices, you can get access to data that those devices send, and it's very collaborative. For our team here at UVA, we can use this infrastructure, we can have facilities management use this infrastructure, community members can use this infrastructure. The data all stay separate, but we're reusing that network infrastructure. And so just to give you a little taste of some of what we've deployed here. So we have a handful of sensors sort of in that Engineers Way test bed nearby UVA. And these are both indoor and outdoor. So one nice thing about having these long range coverage is that we can have devices that are within buildings or sort of in hallways between buildings or along sidewalks, and they can use the same infrastructure. We also have slightly more remote sensors in some of the ponds and retaining ponds around UVA to monitor the water level, so we can sort of understand the ecological hydroshed and how the different retaining ponds are sort of what level they're at. And this can be better manage the water and stormwater here at UVA. But what's really nice, again, about this platform is that it's reusable. And so the architecture allows for end-to-end secured payloads. Different users are going to have different devices. We've deployed these gateways and then the backend provided by the Things Network allows us to collect data. So why am I sort of explaining this LoRaWAN architecture? Well, one interesting thing that comes from this is that these gateways are sort of shared infrastructure, and they're receiving wireless messages and packets from a variety of different sensors. And so this got us thinking, sure, the sensors themselves are sending data, and that can be very useful for different applications. But in the context of wireless sensing, the fact that the signal is propagating through a fair amount of distance in different environments, maybe that is also a source of information that we can use for sensing. And so we've been exploring this new architecture where we're actually taking the existing signals. So if we have these different LoRa sensors deployed in different locations, maybe attached to different physical assets in the environment. But over time, as these devices upload data, the actual wireless channel that they're experiencing is going to change. And that's going to change due to a variety of factors in the environment. But importantly, it is proportional in various ways to that environment. And so if we want to monitor this space, we can, we think, use these wireless signals as a method to do that. And so we already have the devices deployed. We have the gateways. Now we're not looking at what's actually in the data, because again, that's encrypted. We're just looking at what we can observe from the gateway in terms of how that data was received and how that was affected by the environment. So we take those signals, and then that gives us a chance to enable new sensing streams. And so if we go back to our sort of test bed here, where we have a gateway, this is the computer science building, we have a handful of different sensors in the environment. As those are uplinking and transmitting data, we can observe how over time the signal changes because of different changes in the environment. And what's really cool about this, and what I think is a promising outcome of this type of approach, is that as more devices are deployed, the better it gets. Right? So as we have more coverage, different applications come online, whatever the devices are sending, we don't even see that. We're just interested in having that wireless signal as a source of information. And so the actual sensor types might be completely unrelated from what we're trying to monitor. And we might not even have the algorithms when the devices are deployed to be able to monitor it. But with those incoming wireless signals and new algorithms, we can enable new applications on top of an existing infrastructure. And this is in pretty stark contrast to a lot of wireless sensing work. So typically, and sort of like the occupancy detection that I was talking about earlier, typically these systems require that they generate new signals which are then sensed. And so sometimes even the name can be a little misleading. It might be Wi-Fi because it's using the same frequency and same general packet or modulation structure as Wi-Fi, but it's not really reusing what's already there. It's really sort of adding additional signals to the environment and then monitoring with those, which in some cases could be very, very useful. When we think of city scale, having to then deploy additional devices to generate our own signals sort of increases the burden. Not to mention what it does to increasing the crowding of wireless, of the wireless spectrum and the cost. And so we really are focusing on being able to reuse what's already there. And we've developed a pipeline to do just that. So we have our sensors, which are deployed in the environment. As those signals propagate to the receivers, they're going to be affected by the current conditions in the environment. We take what we can extract from the gateway, again, without knowing the actual data of the underlying message, observe things like the signal strength, the signal to noise ratio, the time it was received, and perhaps other features that we can collect. We sort of improve the data stream, and then we've trained an LSTM model to try to characterize what's happening in the environment given what we're seeing from these signal properties. Now, so far, what we've been able to observe is that the signal strength is very dependent on the outdoor temperature. And so you can see that here, the top graph is temperature, lower graph is the signal strength, or you could think of this as how loud the signal is at the receiver. Of course, these are RF wireless signals, so it's not quite really loudness, but it's a way to sort of think about that. And definitely it varies throughout the day as the temperature varies. And so this gives us sort of a potential to be able to do this really fine-grained sort of microclimate monitoring using these wireless signals. However, we noticed something interesting when looking at the data. Some periods of time, the signals are directly proportional. The temperature increases, the RSSI increases. Other times, it's actually inversely proportional. When the temperature increases, the RSSI decreases. And so there's these change points where the way that the gateway responds changes based on the ambient temperature. And so that we had to include that in our processing pipeline, kind of shown here, where we're extracting those features. We use the LSTM model, the long short-term memory model, to handle the time series data. And originally that works fine, except during those change points. And so adding an attention layer helps allow the model to figure out which mode we're in automatically. And so it'll change its predictions based on whether it thinks they're going to be directly proportional, inversely proportional. The simple RNN is for smoothing the output. And then eventually what we have is we have a temperature prediction of what the system thinks the outdoor ambient temperature is, given the readings from the various sensors, the wireless measurements. And so what we found is that this is a fairly accurate way to do sort of local microclimate monitoring. And so we can see here on the left, traces of temperature. This also turns out works for humidity as well, where the temperature and humidity are varying over time. And if you see the blue and orange lines, they're quite similar. And we're able to sort of predict with about a degree of accuracy or 2 to 3% humidity error, the temperature in that local area. And we also here have the green line, which is the sort of weather station nearby, which might be a common sort of fallback, is sort of the sort of city kind of wide station, which is of course similar, but is actually not quite as accurate as what we're able to monitor when we're looking at sort of just that local area. We also looked at what happens if we have multiple gateways. So if we have one gateway outdoors on top of the building, run another one indoors in our lab, if we include the data from both of those gateways, we can improve the error even more. And so if certain applications really wanted to increase the accuracy, adding an additional gateway, which maybe isn't necessary for network coverage, can help with increasing the amount of signal that we get, improving the accuracy. And so this is sort of our current work on using these existing signals to detect properties of the ambient environment. And what I think is kind of exciting about this approach is that as more devices are deployed that use this LoRa protocol, we can actually increase the amount of sensing we can do, because we can run this without having to deploy that additional hardware. And so just by essentially, you could think of this as kind of installing this new application on the gateway, suddenly now we get this potential for this new application to run. So far we've been working on temperature, humidity. Our current work is looking at sort of crowd monitoring. So kind of blending that idea from before with the occupancy detection, where the presence of people also affects these RF signals. Now, there's certainly going to be the influence of the temperature and humidity in how that affects the wireless signal. So we want to be able to essentially subtract that out, and then look for times where a sort of increase in the number of people nearby is affecting the RF signals as well. And so we can understand how movement and people are occupying a space, again, using sensors which might be just monitoring VOCs in the environment or water level depth. And so being able to enable these new applications, that's sort of, I think, where this kind of efficient wireless sensing is going. All right, so that's some of our work on the wireless sensing aspect. I wanted to sort of provide this in a little bit of a zoomed out context. And so this is sort of one piece of the work that my group is doing around different embedded development, energy harvesting, and data management and privacy to form sort of a really robust future of the Internet of Things. And one aspect that we're really interested in is looking at systems for maintaining sustainability in these devices. And so our observation is basically the sort of types of applications we want to enable, these smart cities, smart building applications. The infrastructure we have is meant to last for decades, but oftentimes we build computers and they are replaced maybe every couple of years. With sensors, that can be a pretty bad deal, because sometimes even just deploying the device, getting it where we want to measure something, is actually a big challenge. And so we don't want to have to repeat that over and over again. So we want these devices that can run and be operational and usable sort of long into the future. And we look at sort of three general aspects to that challenge. So the first is removing batteries from the equation. So batteries are great, but they have a fixed capacity. And when that capacity is drained, well, now you have to go replace the battery. So it means you have to somehow find the device and replace the battery. There's, of course, the sort of environmental impact of the battery itself, but just the maintenance overhead of having to do that. So we want to shift to energy harvesting, where devices actually scavenge their own energy. And so as long as they can continue to scavenge that energy and make and do useful work with it, they continue to run. The second piece is kind of what I classify as this upgrading piece. And I think this is really connected to the wireless sensing I've been talking about. The idea that we can take the existing wireless signals, add a new way to process them, and then unlock a new capability is really exciting. We also look at how we can reprogram the devices. So send new firmware to existing devices to add new capability or do new processing on the device, as well as other sort of signals beyond just the wireless signals, where there's actually a really rich connection with the environment that with the right processing, we can do better to figure out what's actually going on in different contexts. And what's, I think, really interesting about this is that over time, as a device is deployed in a particular environment, if we want to shift what it's doing, we now have the capability to reprogram it or change that algorithm so that the same physical device gives us new data as our application needs change. And then the third group is sort of what I call this collaborating direction here, where essentially instead of looking at devices as individual computers that operate on their own or just transmit data, being able to leverage a network of nearby devices, even if they're not necessarily collaborating on the same application, but we can reuse sort of spare compute that might exist. And so once a device is deployed, it's sort of immediately getting older, right? The newer chips are continually better and better, but what's already deployed is sort of fixed. But if we can reuse other compute resources nearby, we can sort of hide some of that inevitable decay that happens as our computing systems keep getting better and better. And so just to sort of illustrate just some of these ideas pretty briefly here, We've developed a range of energy harvesting sensors over the years, looking at a variety of different modalities, different harvesting sources, different use cases, to try to explore like what do these devices need to look like to be effective monitoring, even with energy that they're just scavenging. And one challenge that always comes up with energy harvesting devices is now their operation is dependent on the environment they're in. And that leads to a bit of uncertainty, which adds some risk to using these devices. And so to try to mitigate that a little bit, we've developed what we call the energy harvesting score. And the idea here is really to answer the question, will my energy harvesting device work if I deploy it here? And so this sort of uncertainty makes it maybe we don't always want to use energy harvesting because we're not sure what's going to happen. But what we are working on is this idea that we can try to characterize the environment to figure out how much energy is available and how often is it available, encode that in this numeric score, which tells us something about the physical space. Then we can look at the device, what it needs to do, how often it's trying to collect data, what its power usage is to do its workload, and figure out what score does it need to operate as expected. And so now it just becomes a matching problem. If your environment is characterized to be better and the score is higher than what the device requires, then we expect the device will sort of operate in its predictable, expected fashion. And so this is a way to kind of match devices to environments, so we're not just kind of guessing, will this device work? A separate aspect for this sort of longevity and sustainable IoT is that idea of thinking of devices as a network, as a collaborative group. And I sort of summarize this with thinking about it's okay to ask for help. So today, a lot of our devices are designed in a way that they're completely self-sufficient. They can operate independently of what other devices might be nearby. We sort of imagine a slightly different version where devices can do some of their functionality sort of independently, but as they're paired with this nearby additional compute, performance increases. And so some tasks actually get offloaded to nearby ambient compute resources, which might already exist in the environment. And so you could imagine an ecosystem, say like the Apple ecosystem, where when you buy one product, it fits in. And then as you have more devices nearby, the performance of the entire system actually gets better because they're able to collaborate in situ in the deployment setting. And so again, this is a way to make it so that you can have a device that's got certain capabilities when it's first deployed, but then it actually upgrades over time without having to replace that device. And so if we go back to this idea of sustainable Internet of Things, I think wireless sensing is sort of one piece that fits in here. We can enable these new applications by using these signals which are already there. And if we can, as we develop better and better algorithms for processing those signals, we get new capabilities. All right. So I'm sort of the spokesperson here. Of course, it's really my research group and grad students who really drive this work. Particular shout out to Fatime, who's the lead on the wireless sensing work I described. You can see some of my students from the past few years. And with that, thank you.